Hey folks, we're going to see another example here now for simple harmonic motion. This is actually a past exam question from the 2023 exam for this module. And the three parts of this question that we're going to answer are actually worth 12 out of a total of 20 for that particular question. So this is a good chunk of the marks available. So let's work through it and see what we can get. So the example reads, a block of mass 8 kilograms is attached to a spring of spring constant K equals 200 newtons per meter. It rests on a smooth horizontal surface. That means we can ignore friction, because it says smooth there. When the block is pulled back 3 centimeters from the equilibrium position, it executes simple harmonic motion. We're asked to find the maximum acceleration, the maximum velocity, and the acceleration when the block is 2 centimeters from equilibrium. So let's see how we go about solving this particular problem. Let's actually draw the situation just to so we can visualize it. So here's our spring. We've got our mass there, and it's resting on this smooth horizontal surface. And obviously what's happening is that this mass is oscillating back and forth because the spring is stretching and compressing. And we're given various facts about this. So we're told, for instance, that at time equals 0, we were at a position of 3 centimeters. So 0.03 meters is our position at time equals 0. And we're told that the velocity at time equals 0 is 0. Let's put our units in there. So that's meters, and that's meters per second, because the question says that it's put there and released from rest. It doesn't actually say released from rest. I forgot to write that part down. Okay, but that's the implication there. Our velocity is 0 meters per second at the start. We're also given some other information. We're told that the spring constant is 200 newtons per meter, and we're told that the mass is 8 kilograms. And we're actually going to use that fact straight away, because in order to determine how this thing is moving, well, we've got our formula for the position of our simple harmonic oscillator. It's just given by this xm cosine omega t plus phi. Okay, this is the general formula, which you just need to know. I mean, you can derive it, but it's easier if you just remember the formula. In order to solve this, we need to work out what xm and phi are. We're going to do that using this information about where the block is initially. But we also need to know what omega is. And omega is defined in terms of k and m. So we can write down omega is equal to the square root of k divided by m. That's the definition of omega in this formula. So that's just the square root of 200 divided by 8, which happens to be the square root of 25, which is, of course, 5. And that is measured in units of radians per second. So that's our angular frequency, rather. So we can then substitute that into this formula. I'm actually going to keep the formula general. I'm going to keep using omega. We're just going to remember that it's equal to 5 radians per second. So the question asks us to determine the acceleration. Well, I really need to know what xm and phi are in order to do that. So let's try to characterize what those numbers are based on the information we've got there. So we can substitute in t equals 0, and when we do that, we're going to get cosine of omega t, which is will be 0, okay, plus phi, so it'll just be cosine of phi. So we can write down that x at t equals 0 is just equal to xm cosine phi, okay, and that's because this omega t here, I'm putting in t equals 0, so that goes away. So that's one piece of information we've used. The other piece of information, we can write down that the velocity as a function of time. Well, to get that, I just need to differentiate this expression. So when I differentiate cosine, I'm going to get minus sine, and I'm going to pick up a factor of omega from here. So I'm going to get minus omega xm sine omega t plus phi. That's just the general expression for the velocity. So at t equals 0, again, I'm going to get minus omega xm. Well, sine omega t, so again, the omega t goes to 0, and I'm just going to get sine of phi there. Now, we now have these two equations, but we know what the numbers are. We know what the values are for x at t equals 0 and v at t equals 0. So we can substitute those in to work out the values of xm and phi. So first of all, from v at t equals 0, that is equal to 0. It's 0 meters per second. That's the velocity at time equals 0. And we're told, we just worked out that's minus omega xm sine phi. Well, this actually immediately tells us what the value of phi must be, because omega we know is 5, and xm is going to be the maximum amplitude. That can't be 0 as well. So the only way for this expression to be 0 is if sine of phi is 0. So this actually implies that sine of phi is 0, which tells us then that phi must be 0 as well. Okay, so we've determined one of our constants. We can now return to this formula and put in the number that we know for x at time equals 0 to determine what xm is. So x at t equals 0 is equal to 0.03 meters. It's our initial position. And that is equal to xm cosine omega t plus phi, but omega t is 0 again. T is 0. Cosine phi. Well, I know that phi is 0, so this just becomes xm times 1. And so this tells me that xm is just 0.03. And this is a kind of standard setup. We release our particle from rest at its maximum amplitude, so we end up with the phase equals 0 and the maximum amplitude equal to our initial amplitude. So we can now write down a formula for our position as a function of time. It's just 0.03 cosine omega t. Omega, remember, is 5t plus phi, and phi is 0. So this is actually the formula which maps out our position as a function of time. Okay, let's get back now to the question. What's it actually asking us to compute? We're asked to find the maximum acceleration and the maximum velocity. So from this formula, we can compute the maximum amplitude and the maximum velocity. Or sorry, the maximum acceleration and the maximum velocity. We simply have to differentiate this expression with respect to time to get the velocity and the acceleration. So you can do this using the general form. This thing that we wrote down here, you can write down what the velocity is. We already did it here, in fact, and then you can differentiate this to get the acceleration. Or you can do it with this expression and just get the numbers. In either case, what you'll get is, so if I write down the velocity as a function of time, I'm going to get a factor of 5 from here. So I'm going to get minus 5 times 0.03 times sine of 5t. And then we work out what the maximum value of this is. Well, the maximum value that the sine function can take here is 1. And so the maximum value that the velocity can take will be given by the product of these two numbers. And if we just are interested in the amplitude of that, so if I take the amplitude, maximum amplitude of v, I will just get 5 times 0.03. So that just gives me 0.15 meters per second. That's the maximum velocity. So I'm doing these out of order, but I'm doing them in order of the derivatives here. So this is the maximum velocity. Let's differentiate again to get what the maximum acceleration will be. The acceleration as a function of time, we're going to differentiate that v again with respect to time. So when I differentiate sine, I'm going to get cosine. I'm going to pick up another factor of 5 there. So I'm going to get minus 25. That's the 5 times 5 times 0.03. Oh, put an extra 0 in there. 0.03 cosine 5t. And indeed, if you just compare, this is just equal to minus omega squared x of t. Just that is the formula for simple harmonic motion that we have to solve to get the equations. It's just as a sense check, that's exactly what we've written down here. Minus omega squared is this minus 25, and then this expression is our x of t. Anyway, to compute what the maximum value of this acceleration is, once again, cosine of 5t, the maximum value that can take is 1. So the maximum amplitude of the acceleration will just be given by this 25 times 0.03, which is 0.75 meters per second squared. That's our maximum acceleration. Okay, so those are actually just formulas that we used in the lecture, okay? So we haven't actually done anything too new here. Let's now do the last part. It says find the acceleration when the block is 2 centimeters from equilibrium. Well, there's a couple of different ways you can go about this, and I'm going to show you like the long-winded way, which is actually the way I solved this problem when I saw it first, and then I realized there was a shortcut that I could take, and I felt a bit silly for not taking that shortcut. But in any case, this is the way that I went about solving it. I wrote down the expression for the acceleration. It's equal to minus omega squared times x of t, which is just minus omega squared xm cosine omega t plus phi. Okay, so again, just using the kind of full formula, we can then substitute in our numbers. What I did in order to solve this was to say, well, I know that my x of t at some particular t, let's call it t2, because this is when we are 2 centimeters from equilibrium. So that's equal to 0.02. That's going to be equal to, my xm cosine omega t plus phi. And again, I can substitute in the numbers there. So what I've written down here is the formula, which would then allow me to determine at what time the position is equal to 0.02. And I could solve this to work out what t is. So if I substitute in my numbers there, 0.02, xm we know is 0.03, omega we know is 5, and phi we know is 0. So I could then actually write down that t is equal to 1/5 arc cos 0.2 divided by 0.3, just cancels down to 2/3. And using this time, then I could substitute that back in here to tell me what the acceleration is. In fact, I wouldn't even need to calculate the time and then substitute it back in. As long as I know that cosine of 5t is 2/3, I can substitute that directly in here. Okay, I don't need to go to the bother of calculating the arc cos and then calculating the cos of that. And if you do that, you'll get a value for the acceleration at this particular moment in time. But of course, we can just use this formula directly. And this is the thing that made me feel a little bit silly and actually made me re-record the video, is that I missed this part initially. If I know that the position at my particular time, again, t2, let's call it, and that's the time at which I'm at a position of 0.02, I can just use this formula directly to calculate what the acceleration is at that time. I just multiply that position by omega squared. And of course, either way you do this, you get the same answer, okay? But if I'm going to just plug the formula in there, A at this specific time is just minus omega squared times my position, which I know is 0.02. That's 2 centimeters displacement. So I'll get minus omega squared, which is minus 25. Minus 25 times 0.02. And that gives me an acceleration then of minus 0.5 meters per second squared. Whatever way you do this, you get the same number, so that's fine. But this is how you then kind of use these formulas to determine the acceleration at a specific instant in time, which is what this exam question was asking. So have a go at that question yourself. Make sure you can kind of follow through the logic. I hope it makes sense.